Okay, so today we're going to cover a very interesting relation between the union inequality and PAC learning. So, or learning theory, if you like. Basically, the union bound is a very fundamental property of probability. In general, one of the axioms of probability says that if you have a division of events BI, then the union of the division is equal to the sum. The probability of the union of the division of the BIs is equal to the sum of the probability of each event. Now, the union bound tells you how to handle a case where the events overlap. So basically, if you have a countable number of events, what is the probability of their union? Now, because the events overlap, we no longer have an equality, but it simply equals the sum of the probability of the AI events, but instead we have an inequality. And so just to give you an example here of what we're talking about, say we have an overlapping event. We have a variable x which is continuous, and we have overlapping events. One that the values of x fall between 0 and 2, and the other one is that the values fall between 1 and 3. So 0 and 2 and 1 and 3 are overlapping, and so on. So A3 is that the probability falls between 2 and 4, and so on. So AI are all overlapping, and say that these are the probabilities, so 1 over 4, 1 over 8, so on. So basically, the union bound will tell us that the probability of the union is bounded by this sum. So we can talk about or estimate the probability of the union, although the events overlap. That's where the bound is useful. And the idea of the proof is very simple. Basically, we create another set of events, BI, with union equal to the union of AI, but BIs are a division. And how do we create it? It's very simple. The first BI is A1. Second BI is A2 minus A1. And the third BI is A3 minus the union of A1 and A2, and so forth. So you see, first I take A1, then I take this part here, which is what remains from A2 once I take away A1, and then I take this part here, which is A3 once you remove A1 and A2. Okay. So trying to improve the audio. Is that better? Guy?
Yes, it is.
Oh, very good, very good. So, okay, so this is how I create a different set of events, countable set BI, which has the property that the union of BI is the union of AI. And now I can apply the first rule. So it's the sum of the probabilities of BI, and because each BI is contained in AI, then the probability of BI, the sum of probabilities of BI is less than or equal to the sum of probabilities of AI. Okay, so that's the idea of the union bound. Any questions about this?
No, thank you.
No.
Good. So how is this connected to pack learning? In fact, to agnostic pack learning. So one thing you need to understand about learning theory is the concept of a hypothesis. A hypothesis is the set of all functions we're trying to choose from a model. So imagine that H is a big bucket of the possible models we want to choose from, and we choose one of them as the model of choice. Now, we are not used to thinking about it in that way, but for instance, the neural network will have weights on the edges. And essentially, once we train the model, we have fixed the edges, the weights on the edges. So we chose out of an infinite amount of possible models, we chose one model. So H is the model defined, H is the space defined by all possible weights on the edges of the neural network. Just to give another example, if my models are A plus of the form A plus BX plus C X squared, then my model is, the possible hypotheses are all sets of A, B, and C. Again, I'm looking for A, B, and C that will be the best model out of that infinite set of possible models. So that's one concept that you need to understand. Now, the other concept that we need to understand is the concept of the average loss. So, for instance, if we choose a specific model and we are learning on a training set, which we call here a sample S, then we could, if it's a classifier, we could check on each S whether we are correct or not, and depending on some loss function, we'll get an average loss on the sample. So that's one option or one thing that we have that indicates how good or how bad the model we chose is. It's the average performance on the sample. But there's another one, which is the average performance, the theoretical average performance based on the probability distribution that we don't know. And here we denote it as LP, H. Now, the law of large numbers tells us that if the sample is big enough, then LSH will be close to LPH. Now, this is at the heart of theoretical machine learning theory. So basically, if the sample is big enough, then whatever I see on the sample is similar to what I'm going to see in reality, more or less. So that's an important notion. Now let's see how the union bound comes to play here. So if you look at this statement here, we're basically saying that the sample is such that there is a model in the hypothesis set so that the the loss on the sample and the loss in reality is bigger than an epsilon. So in a sense, this is a not so good or not big enough sample, because for some hypotheses, the behavior on the sample, the LSH, is not representative of the behavior in reality, which is the LPH. Okay? Now, are there any questions up to now?
No.
Okay, great. So now we bring to play the union bound. We say, if there exists such an H, then this probability equals to the union over all such occurrence of cases where H is not representative. So basically, those two sets are equal, right? If some sample is a member of the union, then there exists one. If there exists one, then it's a member of the union. So these two sets are equal. And now you've casted the question of how well the sample represents reality in the language of the union bound, because you have a union of sets, and you're asking something about their probability. This is bound by the sum of the probabilities. Now, each one of these, you can once the sample is big enough, it will get close to the real probability because of the law of large numbers. So if we have H to be finite, then we can now bound this sum, and we basically get a theoretical pack learning result. So basically, a basic instrument in proving theoretical pack learning results is to use the union bound over the existence of non-representative samples. Any questions about this?
Okay. No.
Okay. Okay. So yes. So thank you for joining, and we'll continue next week.
Thank you, Eitan.
Thank you, Eitan.
Thank you.